Let's start with the illusion of control. So I actually demoed or sort of demoed this at CT Pug last weekend. That went completely horribly, considering that I tried a new version of the firmware and I was sick and stuff like that. So this has improved a lot. I'll see how much I can do with the embedded controller on a stage. But let's get going. Who here has seen, tried, or heard of MicroPython before? Okay, cool. So it's something that I just picked up for fun, tried around. It's been rather interesting. Back or sure. So basically, running Python on microcontrollers or any constrained environment. Running Python on a server or even your computer is relatively easy, or even on a Raspberry Pi, but think even smaller than that. Just quick on me, I work at Vast Solutions, hence the shirt, and the other colleagues. And so this talk is not at all related to what I do. And then otherwise, I help run a WASP Cape Town. Every other now and then we do a talk. So if you're keen to do anything around security, let us know. So that's the general outline. It might have changed as I've added slides, but I'll run you through MicroPython, the idea, how it all comes together, the hardware API, which is essentially the core of it, MicroPython versus normal Python and Arduino, libraries. There's a MicroPython web framework as well. And then building MicroPython, I'll talk about it quickly because it's slightly boring, and then move on to some use cases for it. And then I'll focus mostly on the ESP8266. There is a device specifically built for MicroPython, but I quite like the ESP8266, and I wasn't sure if I would even get the board in time if I ordered a Pi board for this. And to use a sort of simplified concept of what it is, it's Python 3 based syntax for microcontrollers, and with the Internet of Things market in mind. Most people going into the Internet of Things might not be embedded developers, so they might not have a good understanding of C or Lua or anything else that is in that space. Why MicroPython? Before we even go into what it is, why would you even use it? Obviously, Python being a high-level language, MicroPython tries to take a high-level approach to hardware, like a hardware API. It's got a nice open source community going. If there's a device that you'd like to link up, I linked up a device that a friend of mine had this week. Found a library for it that someone already had written, so I literally just had to interface with the library, didn't have to write any code to do it. It's easy to learn and read, has a lot of powerful features, and it's not JavaScript, Lua, C, which might shy away some people. And why not normal Python? Why not PyPy? So if I look at the ESP8266 device here that I'll show you later as well, it has a really low amount of RAM and ROM. So normal Python would fill up, even a string or an object in Python would probably take up all the resources on the little machine, and what can you do after that? Most microcontrollers need optimized code, and then especially CPython, a lot of libraries try and cache everything into the RAM off disk to speed it up. That would kill the device. And you can read up on more of the differences if you feel like it. Some of the other differences is it's got its own garbage collector versus the normal reference counting. Classes and objects are not 100% implemented like C Python 3. So this is where I have to stress that MicroPython isn't Python, it's an implementation based on C Python 3. So it's familiar, but you will find differences if you go through the process. And we finally get to what is MicroPython. MicroPython was a Kickstarter project initially around what they called the Pi board. They actually successfully funded the campaign, and compared to normal hardware projects in Kickstarter where they just push for getting the hardware out, they actually set goals for libraries, for functions, for different devices, not just their own device. So the more funding they got, the more features you got with MicroPython, up to the point where eventually the project was fully funded. They continued with the development, and other people started picking up with different devices and adding their own things onto it. And I'll also talk briefly about the Pi board a little bit later. So the gist of it being a tiny implementation of Python running on something like a PIC or Teensy or even BBC's microbit or their own Pi board. Some of the features in MicroPython, the first thing is it actually has a REPL. So you often with microcontrollers, and you see this with Arduino, is they'll have an entire tool chain and IDE and everything, but on each completion of your code, you pretty much have to flash it to the device to see if it works. MicroPython helps with that because you can load the firmware onto it, the basic firmware, and start interfacing with the REPL. This is especially powerful for if you're doing prototyping. If you have a device, you're not sure what each pin's doing, you link it up to a device running MicroPython, and you use the high-level API to start hitting the pins, see what it returns, what you can send it. Auto-completion, auto-indentation. So for first-time Python users, that helps a little bit. Not sure what the class or function contains. It has a paste mode, so instead of you can build all of your code and ship it as a firmware upload, or you can just copy scripts that you've written. If you just want to do some quick prototyping, it has a web interface as well, hardware API, as I've mentioned a couple of times, and you can actually also do assembler on it if you want to interface directly with the hardware. And then it also has a special variable, the underscore, so when you're working in the REPL, you do something like 15 plus 5, it actually captures it in a temporary variable that you could use afterwards. So I've spoken about the hardware API already, and a lot of the core philosophy behind MicroPython is abstracting to some extent you from the hardware in an easy to use way. So you have UART, just general input output pins, I2C. You have a whole bunch of pre-built APIs that you can use across different devices. The API will change slightly, but if you're using the machine, you'll usually have the same features or behavior across all of them. The Pi board is a bit different as it has its own Pi board functionality and API that's obviously a lot more supported. So if you want to get off the ground quickly, you go with the Pi board. Otherwise, you've got everything at your disposal already and a lot of documentation and resources to actually use. Compared to Arduino, with Arduino, you've got the IDE. It can interface directly with Arduino. MicroPython is mostly just the language, so it puts a bit more of the effort on you. And there's a couple of others. I'm not going to go into Arduino too much because that's obviously not what I'm covering. And as I said before, the one thing with something like the Arduino is that it uses compiled code. So if you are trying to just debug something quickly or see what kind of functionality it has, MicroPython's easy to just open up the interactive REPL and just go through the language. And a lot of the libraries that Python already has are too big for most of the devices to actually use. So if you go on PyPy, you'll find a lot of these UPIP or URLlib, so micro libraries, if you can call it that, that they've started implementing where the normal library won't work. So some of normal Python 3 is interchangeable, but most of it not. And also for optimization for lower RAM usage, they've gone and rewritten or basically made smaller compressed libraries to use. But I mean, like a lot of things seem or are very familiar to any Python developer already. Although multiprocessing is one of those libraries where on an ESP8266 that's rather wasteful. So it depends on the device once again. And that's also a big thing with MicroPython is that the documentation that you'll need to read most of the time specify the device. Don't just read the general documentation. And I've talked about machine before. There's also a MicroPython specific library, a network library for using most of these. A lot of these devices have wireless LAN built in, or some kind of network access. So it's easy to interface with that. There's an easy to use API, and then also the UC types. A quick and interesting thing is that someone actually already wrote a Flask-like web framework called PicoWeb. Now, as much as I've tried, I don't know if I'm doing something wrong, but I can't actually get it to run. So the jury's still out on this one. And it can actually also run in CPython 3.4.2 or higher, but you do need the MicroPython libraries that it uses, and it's asynchronous, much like the syntax looks like Flask. Oh, sorry about that. So yeah, obviously the idea being close to Django or Flask or Bottles so that you could adopt the existing Python developer mindset with this little framework. For most of these devices, this is probably also overkill, as you can just write your own little web server and just serve static content. But if you feel like templating and using JSON and a little more advanced features, this is where PicoWeb comes in, and I will one day get this to work. That is a challenge I will have to set for myself. So MicroPython still isn't at a point where you can easily just get it off apt-get or something like that. Some people do, or MicroPython, the organization itself, will have certain builds for it that you can download. Some of them are often quite old. So generally the idea is to build it yourself, clone the GitHub directory, GitHub page, and then with all the needed packages to build it yourself. If you're doing it on a Unix-based system, you can easily get used to the language without having to flash to a device or using a device. You will not have a lot of the microcontroller-based libraries like network and stuff like that. So it depends on what you want to do with it. You could use normal Python on a Unix system if you have enough hardware, and the builds go up quite high. I'm still trying to figure out if it's caching something, but specifically where I talk about the 4.5 gigs, is not for the Unix or any of the other devices. It's specifically ESP8266 toolchain that's taking up all the space. And I'm still working on getting it working in Alpine Linux as well. Building it for Unix is fairly easy. You install a couple of libraries and packages, and always good to just get all the sub-modules for it, as well as it uses stuff like, I think it's Berkeley database and a couple of other things. The AXTLS is an embedded SSL library that it's dependent on, and then you make it, and it's if I you can either do a normal make or a make build, and it will actually also so if you do a normal make, it's just gonna compile all of the C code. If you do a make install, it'll actually also put links to the executables in your user/bin as MicroPython. And as I didn't actually mention before, they also have their own version of pip called MicroPyp. So once you've got it built, you can just run it interactively. As I've said, it has tab completion, and then for instance, you can use their own version of pip, much like you use the current version of pip without all the advanced functionality. They have worked virtual env into it as well, so you could get something like micro requests, and it's fairly simple to use. So possibly useful for developing modules for it or libraries and just playing around with it. But that's not sort of the key strength of MicroPython. So if I move on to the Pi board, this is the board that they actually built everything around. The Kickstarter campaign. It's got a little bit more hardware than most microcontrollers, like the ESP8266. It has a SD card slot. It has USB, mini USB already on it, and Wi-Fi, accelerometer, and it's fairly easy to program because of the hardware API that it has, PYB. And you can put, it has some LEDs on the board as well, so it's easy to get going with lights flashing, and they have some hardware that's already compatible with it. So that's probably the easiest way to get going. That's accessing both the LED and the accelerometer, and that's sort of the hardware that's running on it. It's got 24 input-output pins, a couple of LEDs, 3.3 volts, micro USB, as I said, 96 megahertz CPU, and about 128 kilobits of RAM. So still a small device, but fairly powerful for something like MicroPython to use. And if you are not quite comfortable with hardware, it's probably the first place to start and easy to get going. And now to the more interesting stuff for me, at least, is the ESP8266. Anyone know of, played with it, burnt one out, broken it, thrown it in a field with 2 AA batteries and fetched it a week later and found what might be on it? So if it's based on a Chinese company's designed, I think they're called Espref systems. and the basic chip has both Wi-Fi and input and output pins on it. So the Wi-Fi part of it is what gave it such quick notoriety. Initially, people actually had to use Google Translate to get through the Chinese documentation to actually even do anything with it. But considering that you can pick up the device that I have and a couple in my bag are between $1 and $3 per device. The ESP01 was the first version they brought out. A bit of a pain because if you're not keen to solder and build your own stuff and work with a breadboard, then programming it is a bit of a pain. As it moved on, it got more pins, and then other companies also started adding stuff like USB to UART on it. Some of them you get with Arduino also connected to it, so you could expand the pins. And it's got a 32-bit, 80 megahertz CPU on it, single core. You can put it up to 160 megahertz, 96 kilobits of RAM, of data RAM, and 64 of instruction RAM. And obviously has Wi-Fi with WPA, WPA2, and WEP, 16 input-output pins, and UART, and a couple of things. So in terms of like Internet of Things kind of devices, this is great. It's really low power. You can run it off two AA batteries if you really wanted to. Lots of pins to work with. Can run a web server on it. And when you actually buy it, generally, depending on if you buy one of the, like the device that I have, generally the other companies will flash it with the Node MCU firmware, which is Lua based, so a Lua scripting engine, but that's not what we're here for. So the device that I have is based off this. It's a D1 Mini, and I've just used this as it sort of shows you all the pins and stuff like that, which is really useful when you're actually trying to program these things. You have to bridge, as much as there's a hardware API, you still have to bridge a little bit into the hardware world and just understand which pins you're actually going for, unless you actually want to put a wire on each pin and start going crazy with LEDs. And then, as it says on the GitHub page, the ESP8266 port is actually experimental, and they use a cross-compiler and also a open source building tool chain to actually do it, which is a bit of a pain, but when you get it working, it's wonderful, and has a whole bunch of features which are useful to us. For instance, it has support for the NeoPixel LEDs, which I'll show later, and you can do HTTP requests with it. You can even run the web REPL on it and then interface with it from a web browser to the device instead of using a serial connection. And building it is a bit more of a process. You need the pFalcon ESP Open SDK based off the SPRIF system's own proprietary one. And it takes a while to build and has a lot of packages it's dependent on. So I'll rather just run through this. Then when you actually get to building it, you have to also build the Empire Cross compiler, and then eventually actually get to the ESP8266. Once again, the embedded TLS library and make, and then you end up with a firmware combined.bin file, which you then can flash with ESP tool, which is a great Python tool for flashing the ESP8266. And then hopefully you'll have a working MicroPython on your ESP8266. And as I've said in the past, when you update your Git, sometimes this doesn't go that well, especially if you don't recursively update all the submodules. It goes horrible. Um, so a couple of things, less modules, doesn't have that PyBoard API, and you can obviously set the frequency to 160 megahertz, but I haven't used that myself. I haven't seen the usefulness for it now. So I'm going to go into to a bit more of a practical demo, and we'll see how that ends up. Goodness. Okay, so why it's saying that is I've got a web server running on it, and I didn't control C it before I did a soft reboot. So the address is already in use, so I'll have to actually reset the device. But before we get there, this is the ESP8266. It has its own bunch of classes and functions that you can use. And a lot of direct, you can actually interface the memory yourself. Another useful thing to note is that you can actually check the firmware from the device and compare it to after you flashed it, which gets really useful. If I do a quick demonstration. So I don't know if everyone will be able to see this, but it has a copy-paste function, which will also actually check your code for indentation and stuff like that. So I hope everyone can see that. I'll do it on the webcam now as well. Not working. Of course, live demos are the best. Just give me a second. Don't change any of that. Success. So what I've learned the hard way is often, especially with MicroPython, switching the device on and off again actually helps. Or, as I did 5 minutes before this talk, reflashing the device with the old firmware also helps if you've really screwed it up along the way. So onto a bit maybe of a more interesting demo. See if this works as well. So in terms of actually programming it and using it, if we go to the ESP8266, except for all the C code, it has a build and a... So the build directory is usually where you'll get your firmware from. I like building it in Docker because I can throw everything away by just destroying the Docker image and rebuilding it. But if you have a look, it has a scripts directory, and you'll see a main.py and a boot.py that I've added on. That's generally the idea when you end up building a device that will actually start running when you restart it instead of interfacing it with UART and then programming it. So I've dropped a bunch of code in main.py and then referenced that in the boot.py. Also, if that really doesn't run, you can actually go to the modules directory and screw with _boot.py, and eventually it'll work. That also gives you an idea of which modules are available. So by default, the WebREPL, OneWire, Flash, BDev, all of that except the BMP 180 modules are already in by default. I added BMP 180 and I'll show you why in a bit. So when you actually build it, the scripts.py gets added to the firmware and then you flash that to the device. And when you restart it, it'll read the main.py and run that, if you've written it correctly, every time you give power to the device. So, you know, in an Internet of Things kind of environment, that's how you probably want to do it, is if the device loses power, you plug it in again, starts up, and it's ready to go. So we'll have a look and see if that works. And I really hope that my colleagues don't remember what that password was. So that's just a little demo that I built for today. I was talking about that BMP 180. And let's see if I can actually get it to show on the webcam. If you have a look, that little device right next to the ESP. So I've got a, much better. At the top, I've got a LED NeoPixel ring, and then I also have the BMP 180, which gives you both, gives you a temperature, pressure, and altitude readout over I2C. So a really nifty little device, easy to interface with on the ESP8266 with that module that I talked about. And then I have 3 of the pins set up. So if I trigger the pins, which most of you might not see, you can actually set it off on the device. And that's the kind of things that you can do right off the bat with the ESP8266, is write a little web server, and I will get back to that. So for everyone who didn't see it earlier on, who was sitting more to the back, I got the LED today only, so it's been rather experimental, and I luckily got it to work, so it's not in that demo. So do that again. So if people in the back can't see, that's the kind of stuff that you can do with a short amount of code. Simply assign the pin to the NeoPixel driver, and then give it a tuple of the colors. And this has gone through a couple of loops based on which LED it was. And some timing. We actually changed the timing to work with the camera. So in terms of like being a Python developer, it's easy to understand the documentation and quickly write something like that. This was the little web server, all very quick code that I wrote, so none of it's probably very good, but you know, it's 74 lines of Python. It's fairly easy to get a little web server going. One of the stranger things that I found that with this specific device, and I suppose depending on which dodgy Chinese website you use to order these from, beyond 80 lines, you can't actually copy and paste it into the REPL. It'll just give you errors saying that you've made syntax mistakes or that the keyboard interrupt is wrong or something like that. So obviously, like I've said earlier, that the ESP8260 build is experimental. Most of MicroPython, I would be of the opinion, is experimental. So keep that in mind. And for most people, in the long run, actually going and writing the C code, Arduino, you can use the Arduino tools to also program an ESP8266. So in the long run, if you're worried about the resources, maybe writing it in C or something else is a good idea. But if you want to get off the ground quickly, if you want to just prototype some stuff, or even if you don't care if it's running lean or not, MicroPython might be a good idea. I don't know how much time I've used. A little bit of time. Okay. That's pretty much, I think, what I have to say. I've put on a lot of resources. If anyone knows Adafruit, they're excellent resources on their website. Lots of videos, documentation, and their devices easily interface so far from what I've found with the ESP8266, making it easy. The kind of things that I do in the future with it is using, which is in my bag, something like an Arduino. You can communicate via UART to the Arduino and then run code to then further break out, use the pins on the Arduino to do more hardware, where the ESP8266 has 12 pins and you might need more, then you could do something like that. Beyond MicroPython, if you go slightly more expensive in terms of devices, I mean, a Raspberry Pi runs Python. If you look at something like a Domino.io, which runs OpenWRT, probably not a need for MicroPython. So it's a bit of a niche in between, like paying $2 for a device to actually spending $20 and up. And otherwise, any questions? Oh, and I'll stick around if anyone actually wants to have a look or has crazy code that they want to run on it that I haven't thought of.
Thanks very much, Christo. That was very interesting. I've got some Take-A-Lot vouchers for any questions. I just had a look, and we should also speak to Take-A-Lot and ask them if they can stock some of the ESP8266s.
So on that, the ESP8266 is available in South Africa. So off the top of my head, Communica sells it, but buying it off AliExpress is going to cost you 20 to 30 Rand. Buying it here is going to cost you 80. So it's that wait 4 months, potentially get it stuck in customs, or pay 80 Rand. So it's that kind of thing. Maybe for the sensors, buy it overseas and have it shipped in. The ESPs, maybe buy it here. And specifically look for the D1, and then there's another one that I can't remember what it's called. SensePost recently did their bad USB talk based on one of the ESP8266 models.
Okay. Any other questions?
So my question is just what's the kind of latency or the kind of guaranteed latency you get with MicroPython? Obviously, if you program in C, you can kind of do things at microsecond level.
Yes. So, like for instance, if you're doing audio processing, it's not going to be good. So you can, I haven't got to that point, but they have decorators that you can put on functions to run faster or more natively based on the architecture, but that will also be based on the architecture. So it'll be based on the device that you have. But probably C if you want something real-time fast, like for instance, audio processing, image processing. Hi.
A quick question. I noticed when you run the interpreter, it tells you if main.py exists or not, and it runs it if it runs it. where do you put main.py? Is there a file system? How does that happen?
That's, yeah, I should have probably mentioned that there is a file system. See if I can get to it. So there is a basic file system on there is a basic file system. You can change directory, remove, create. I think it's a VAT file system. It depends on if you're using the flash on it or if you're using a SD card like with the Pi board. But I haven't looked into that a lot. Most of it was just running code. The main.py is in a directory depending on which device you're using. But mostly all the devices will have it in a directory called scripts. And you'll obviously put it in there, build the firmware, and then flash it onto the device. I'm not sure where on the device it actually flashes it, but I assume it's after the firmware, the basic executables, it puts it on the device as well. It sort of does, they talk about some kind of compilation or optimization of the code that you put in there. How that works, I'm not 100% sure.
Okay, I think we've got time for one more question.
Do you have any advice for someone? I'm guessing you're from an embedded software background yourself. Do you have advice for someone who's in a pure software environment now with a background from engineering, and how do you personally apply this?
So let me start with, I have no background in embedded devices at all. So this has been a bit of a learning experience for myself. I have a little brother who's second year engineering, and he helps me understand some of what I'm doing. Otherwise, I read through the documentation, and I think that's the core idea and strength of MicroPython is giving embedded kind of development to devs, normal devs. So I have a friend who does embedded development, and the kind of stuff that he told me is that long-term, or the kind of stuff that they would do in production wouldn't be something like this, because the firmware, when it's compiled, let's have a look at how big it actually is. It's fairly big for embedded device, where if it's compiled C, it's tiny. So to be honest, I still don't know that much about hardware, but it helped me learn it a lot quicker. And I think for someone who's not of that background, you can pick it up quickly. The documentation is straightforward enough. And the kinds of devices that the documentation are on are fairly straightforward. So the little pressure and temperature sensor gives you a digital output, so it's easy to work with. It's not like far out there, but I'm sure you'll be able to pick it up quickly. The bolt system and stuff is a bit of a pain, but when you get there, it's a lot of fun. You can quickly get going with like the LEDs. The LEDs I got 2 hours ago, and it's working. So that should give you an idea.
Is it a quick question? Okay, quick question, because lunch is...
Cool. How did you find the impact of using MicroPython on the system in terms of power consumption and duration, or battery drain?
So I haven't looked at that a lot yet. The device as a whole is very low power. I'm not running it at 160 megahertz, the CPU. So I'll have to come back to you on that. So most of the time I've been powering it off my laptop or a power bank that I usually charge my phone with, which could run it forever. But 2 AA batteries, I'm sure it'll give you a week's power, depending on how intense your code is. If you're going to write loops that clock the CPU the whole time, then you're probably going to run out of power. Also consider the wireless LAN will also drain the power, and driving, depending on the how you set up your devices on it. But obviously MicroPython is probably a bit more inefficient than running C or Arduino or something, so I'd assume that it would use probably 1.5 times what Arduino would do, or something like that. I'll have to look into it. I'm thinking of dropping some in a park somewhere and seeing if people connect to the AP, or why not?
All right. Well, that was a very interesting talk. Thanks very much, Christo. A round of applause. Yeah.